Can you see the can you read at the screen? I mean the is the text
Can
is
sir.
can
Can sir.
okay. So we start with the direct current circuit. Okay, with direct current circuit, we start with the electromotive. Sorry, yeah, electromotive force. So electromotive force essentially is the power source of the battery. I mean, it's the battery itself, the power to push out to maintain the potential difference and the supply current to the passenger circuit. It means that a source of power to push out the electrons and to maintain the potential difference. Okay. Um, this is only the force that we are not counting in the Newton. Okay. Only physics force that we are not measured in Newton. Okay. So what is EMF? EMF is the force, electric source, is the amount of electric energy gained by each coulomb of charge supplied by the source. Okay. Uh, I'll have to scroll this. I think I should put. Oh, yeah. Okay. Should put over here. Can you see? Okay. I think it's better. Okay. So it's a source. Okay. It's a source amount of electric energy gained by each coulomb of the charge supplied by the source. So E equals to work done by work divided by the Q. Okay, Q is in the column charge. So work equals to Q times the E. Okay. So next part where the W, you see if is the W is any of the source. Okay, supplied by the source. W is energy supplied by the source. Q is a charge flow to the electric source, and E is the EMF. Okay, so power of electric source PS, power of the source in PS. So we came from WQ equals to IT. I stands for current and T is the time. So from there we have the equation that before we have W equals to QE and Q equals to EIT. And power supply by the battery is W over T E divided by T. So we can solve T over here. Then we have EI. So power is depends on the EMF times with the current. For example, if EMF is 1.5 volt and the current is 0.3 ampere, then the power supply is 0.45 watt. Okay, so EMF is 1.5 volt. Remember, EMF, even though it's a force, but the measurement unit will be in voltage, and the current, of course, in the ampere, 0.3. So the power supply battery will be 0.45 watt. Potential difference is the potential between 2 points in the circuit if energy dissipated by each coulomb of charge, which flows from one point to another point. So V is work divided by the charge, and work equals to Q times V. In the circuit below, the potential difference across the bulb is 1.2. Can you see that the bulb over here, this is the bulb or the load is 1.2 volt. It means that for each column pushed through it, 1.2 joule of electrical energy is changed into another form. So the uh, every column, one column of column pushed towards the bulb, it will change into 1.2 joule of energy. Okay. Power of load. Okay, power of load, electrical load is convert electrical appliance. We convert electric energy into another form of energy like that, mechanical energy or sound energy. If potential difference across V and the current flows in the circuit is I, the current charge flowing of the load is given by QIT. So this is deriving the P equals to IV from W over T, VIT over T, then VI. Okay. When the battery is applied current, some energy wasted, of course, is efficiency will be not gaining not will be 100% of efficiency. So for example, battery at EMF 1.5 supplying a current, the potential difference across the meter might be only 1.2 due to voltage across, and the resistance of battery is 0.3. So the resistor will hold up some of the voltage of the EMF. We may take out around 0.3. We end up with 1.2 volt. Internal resistance is when relative a battery is applying a current, its output potential difference is less than the EMF, of course, right? It will be less than the EMF. Mathematically, it can be treated as additional resistor of the circuit. So we can assume that there was one more internal resistance in the battery. Okay. So power supply of the battery, power supplied by the battery equals the power released in the load plus the rate heat in the internal resistance. EI, okay, power released by chemical reaction equals to VI, power liberated by the external circuit, plus I squared R, power dissipated inside the battery. Then we came up with E equals to V plus IR. This is very common formula that you have seen before. I see, because this is all about the EMF. Okay, V is the voltage supplied and IR is the power dissipated. Okay, so if the resistance of the load is varied, the terminal voltage will be varied with the current as shown in the below. So the output potential different in both and the current. So you can see that the gradient will be going down because of the load, the balance of the load between the voltage and the current. Next, the drive cell with EMF 1.5 volt is connected to series with resistor and battery. So we have a EMF over here. Okay, so, and then we have internal resistance R, and we have if the current flow high, current flow 3.0 ampere flows, potential difference across the dry cell is 0.42 volts. What is the internal resistance of the dry cell? Okay, so it says that the dry cell itself is 0.42 volts. Okay, so what will be the internal, what will be the R? So 1.5 volt from E equals to V plus IR, 1.5 volt. This is the EMF, 1.5 volt equals to 0.42, the voltage of the given by the EMF, because of the resistance, and 3.0 R, 3.0 R because of the circuit itself. So R will be 0.36 ohm. Okay. State a situation where the potential difference across the terminal of the battery is same as the EMF battery, less than the EMF of the battery, and more than the EMF of the battery. So I think it's analogous if you have a bulb over here. You draw a light bulb. Okay, and then you shield it with a filter around it. Okay, and then this is your eye over. Okay, so if the potential difference across centimeter is same EMF for the battery, so it means that the light path, the intensity of the light they pass through towards your eye here at this point and this point is same. Okay, so it says that the filter over here will be actually is a zero filter, right? It is not filter anything. So there's no current flowing through the battery. Okay. So if it has less than, let's say we have a potential difference, it's less than the EMF for the battery, it means that they have a less. It means that the light that goes to your eye is lesser. This side has bigger and this side is smaller. I mean the intensity is dimmer and brighter. This side is brighter, this side is dimmer. So it means that over here we have a intensity less. It's not zero. Okay. Next part is common sense when potential difference is greater than the EMF for the battery when the battery is being charged. During the charging process, the current flowing against the battery, of course, the EMF, I mean where is it? This is where you have a charge. The V is higher than the EMF. Okay, V is higher than EMF. It means that the current is flow towards the battery, and the power is flowing against the battery and it's actually charging the battery. Okay, so the battery is charged actually if the potential difference is greater than maybe V is bigger than E. Okay, Kirchhoff law. First law, the sum of the currents entering any junction must be equal to the sum of currents leaving of that junction. So it means that any current going in, okay, the three current that's going in, the sum of the three current, it will be equal to how much the currents flow out to a junction. So I plus 2, for instance, I1 plus I2 will be I3 plus I4 plus I5. Or we can write as summation of I equals to 0. Left going in equals to going out. You can use this diagram. So I1 plus I2 equals to I3 plus I4 and I5. Second law of Kirchhoff, it says that summation of voltage, potential difference, it means that potential difference across all elements around a circuit must be 0. So how much the voltage supplied by EMF, how much total supplied by EMF equals to how much voltage drop or how much voltage taken out by the resistor. Okay, this is consistent with principle of conservation of energy. For example, we have here one loop. This is one loop. We call this one loop. Okay, there are 1, 2, 3 T resistor. There are two EMF, one EMF over here and one EMF over here. So how to determine the direction of the loop? You can see that it doesn't have any numbers of E1 over E2, so we can assume that it will be clockwise or anti-clockwise. It's easier if you have a number like E1 is 14 volts and E2 will be like 5 volts. So you take as a majority. So this is E1 is positive to negative, positive to the right side. So moving in this way. The current moving this way, but it was uh it was uh opposed by the E2 with 5 volts. So 14 minus 5 will be 9. 9 volt of opposed by E2. Okay. Let's say we have a working example over here. So Kirchhoff law was executed. What is fundamental law associated by Kirchhoff law? So for this instance, we have 8 volt EMF on the left side. In the middle, we have 4 volt in the middle, and on the right side, we have 10 volt on the right side. Okay, so this is a two loop circuit. So this side we can see that it's positive towards up, but the 8 volt is positive towards up over here. This is positive going down, and this is positive going up. So for the first loop, it shows that in this way for the first loop, and the second loop it looks like it going in this way for the second loop. Okay, so this is you have for the loop 1. Okay, loop 1, 8 plus 4, or for the the second law of Kirchhoff, 8 plus 4 equals to negative 4i1. 4, 8 plus 4 minus 4i1. Where is it? The alpha? Where is 4i1? Is it 4? It is like 2, right? Or is using another? This is IR. Loop 1 is 2.0. 3, 6, y times 2. 1. Oh, yeah. 1, 2. Okay. Now I see it. Okay, so actually 8 plus 4 minus with R1, I 2.0, this is I1, because I1, it ended here, okay, and then this side also I1. Can you see the diagram? Okay, can you see the diagram? Okay, minus
Yes,
with one more I1 is down there, 2.0 I1, and then we have R5. R5 is named as I2, so minus 4.0 I5. Okay, 4.0 I5. So yeah, you have 2 plus negative 2 plus negative 2, you have negative 4 is correct. Okay, so it's equals to, this one equals to 0. And one more for loop number 2, it is 10. We can start with 10. 10 plus with 4 in the middle, minus with, for this one we are using I3. I3 is a 3.0 I3 minus, this is also I3. This is negative 3.0 I3. And in the middle we have negative 4.0 I2 equals to 0. Okay, so you end up with two equation, and one more. Remember I1, you're over here in this junction at A. At the junction at A, this is I1 plus I3 equals to I2 at the junction. So I1 plus I3 equals to I2. So you have one equation, second equation, and third equation. If you work up everything, you end up with I1 is 1.0 ampere, I2 2.0 ampere, and I3 is 1.0 ampere. Okay, then you can solve all those voltage and the current. Okay. Potential divider is to get the fraction of the voltage. Okay. So let's say you have a voltage, let's say this is diagram, you have a very large voltage at this side. You want only a fraction of voltage on this side. So this is V, very big V, and then you only want a fraction of it. To get that, let's say, for example, like this is 40 volt, and you only need like 3 volt from that 40 volt. So you can use the voltage divider by using this formula. V out, it means that how much the V at this side, okay, equals to R2 over here divided by R2 plus R1 times with the V input. For instance, let's say from this situation 40 and 3. So we need 3 volt and we have R1 R2 divided by R1 plus R2 times with the 40. So you have to make combination of R2 plus divided by R1 plus 2. Then you can find the voltage of 3 volts coming out. Conversion of galvanometer to ammeter. You can use a galvanometer, okay, to convert into ammeter. You connect to a resistor we call as shunt R. So galvanometer for ammeter, to change it to ammeter, we just connect a resistor we call as shunt parallel to the galvanometer. Okay, so galvanometer convert into ammeter. We have to galvanometer over here, and we are connecting a resistor over here, and then we made out all this thing is called as ammeter. Okay, so the formula over here that we use is Vg equals to VRS. So Vg over here, Vg equals to VRS. The voltage of Vg, because it's in parallel, Vg equals to voltage of Rs. So you can V and equals to IR. So IR over on top will be equals to IR on the bottom. Next, we want to convert galvanometer to voltmeter. Okay, if we want to convert galvanometer to voltmeter, we have to connect a resistor that is in series with it. Okay, so galvanometer connect to a resistor. Okay, then the whole thing over here will be a voltmeter. Okay, so using the V equals to IR, and I, the current, because it only one current is flowing through I, and these are R of the galvanometer plus R of the resistor. Okay, potentiometer. Remember when you do your experiment, potentiometer, you have a 100 centimeter of wire, and then you can measure the voltage. The voltage of the, you have a 100 meter wire, and then you have a jockey, and then this voltage premier will be equal to the voltage at the secondary down there, And if the voltage Vp equals to Vs, the galvanometer will show a 0 deflection. Okay, so potentiometer is when the top equals to the bottom and the galvanometer shows a 0, so you can make a calculation how much you make. Actually, you are making your own voltmeter. Okay. So this is basic principle of the potentiometer. Okay, and we can compare two cells of E1 and E2. Actually, if you want detail about potentiometer, it has a very a lot of situation, a lot of either you have a resistor down there. If you have two resistor over here, and then you have a switch. Okay, there's a lot of to talk about it, but I think we can. This one has been discussed before with you. Okay, such as this one, you have E1, you have E2, you have a switch over here, you have a primary circuit, you have a secondary circuit over here, one circuit, second circuit. Okay. This one I think we have discussed before. I'm not going to discuss about this potentiometer. Okay. This is also potentiometer. Measuring EMF for thermocouple. Thermocouple is when two different wires, okay, different wires are joined together. There will be when they heat up, they will be giving us some small voltage. Okay. Comparing resistance. Okay, Wheatstone bridge. Wheatstone bridge is this is done in your experiment. Wheatstone bridge. This one has been done right.
Got, sir. Got, sir.
Got right. Okay, I'm not going to discuss this one. Okay, so meter bridge. This is in your experiment. Meter bridge you have done before. You can determine how much is the how much is the resistance of the X, okay, by using a Wheatstone bridge. Okay, and lastly, finish already. Okay, so that's all in the DC. Okay, this is good. So mostly it's about the theories of what is inside the battery, what is the EMF of the battery, the voltage, the current, and then what is the Kirchhoff law. It's mainly about Kirchhoff law. Most of the question is about Kirchhoff law. If you can answer Kirchhoff law, you'll be safe. Okay. Make sure you have done Kirchhoff exercise of Kirchhoff law, lots of exercise in the Kirchhoff law, and you know that sometimes the loops are some EMF of the battery will be opposed the loops that you are making. Potential divider is also a favorite question in the STPM. An example, this is example of a galvanometer. Okay, galvanometer. Okay, just remember, how to remember either emitter. Okay, let's say emitter. Emitter, if you put into a circuit, you have to, let's say you put in a circuit, you have to connect in series. Okay, connect in series. But inside the emitter, the thing are connected in parallel. So this is in parallel. Okay, so emitter are connected in series to a circuit, but inside the emitter, the galvanometer are connected in parallel. Okay. For voltmeter, you cannot see my diagram. Okay, how to? Okay. Yeah. I remove all this thing. Okay. For ammeter, okay, ammeter will be connected in series with the uh the with connected in series with the with all the things, resistor and battery inside. So this is connected in series. Okay, but inside the emitter, okay, the galvanometer are connected in parallel to the which we call this a shunt. Shunt. The resistor we call as a shunt. So this is connected in parallel. But in voltmeter, it was connected in series. I mean in parallel. Okay. So to find, sorry, not this way. To okay, it's connected in parallel, but inside the voltmeter is actually a galvanometer that is connected in series with the multiplier. So this is in series. Okay, so remember, if you confuse, either inside emitter or inside voltmeter is series or parallel, you just remind yourself either emitter is connected in series to the circuit or parallel to the circuit. Then the thing inside will be opposite. Okay. Okay, I think we can stop here for DC current. Okay, any question? Anyone? Sheridan,
No,
Kashika,
sir.
Usha, Abi?
No, sir.
No, okay.
No,
So
sir.
okay. So
No
see you
questions,
tomorrow.
sir.
See you tonight. Bye.
Okay, sir. Thanks, sir.
Okay, sir. Thank you, sir.
Thank you, sir.